Hello, I'm gonna do a short video here on sound waves, and in order to get started on that, I want to just kind of quickly overview the two broad categories of types of waves that we're going to be talking about throughout the course. The first is mechanical waves, and mechanical waves are waves that are propagating or moving through physical materials. So molecules are in motion. If I've got examples there, sound, water waves, earthquakes. That's also ripples in strings or springs or slinkies like this. If there's physical material trying to vibrate, it's going to exert forces on molecules that are next to it, and those molecules are getting kind of dragged along maybe, and that's what causes the wave, the vibration, and for one particular place to turn into a wave that actually moves through space. So mechanical waves require physical materials. The second type, which we're not going to be covering in this video, just to clarify that there is a second broad category of waves, is the electromagnetic waves. And these are where electrically charged particles, protons or electrons, although it's typically electrons, are vibrating around at a high frequency, which causes ripples in the electric fields and magnetic fields that surround them. And if they're vibrating at a high enough frequency, we end up seeing them in terms of visible light. Visible light is electromagnetic waves. They're ripples created by charged particles vibrating at extremely high frequencies. Radio waves, infrared, all those other things as well are EM waves or electromagnetic waves, but I'm not going to talk about those today. It is tempting to think that radio is some sort of a sound wave, but it's not. Radio itself is an electromagnetic wave that you need a circuit to sort of decipher and turn into sound that then comes out of a speaker. Moving air, which is a physical material, so it's a mechanical wave. Now, for mechanical waves, there are two different ways that they can move or propagate through space and time. The first is called a transverse wave, and transverse waves, as we can see in this diagram here, are essentially if I'm holding a slinky, which I wish I could. If we were in the classroom, we would have this slinky here, and I would show that if I give it a ripple, you can see over a long distance, if I give it a displacement, maybe up and down, let's say, that as I move one part of the slinky up, it's going to stretch the part next to it with it, and it's always going to trail behind whatever I'm doing because the slinky's kind of slinky. And so as I move an up and down motion right here, the wave will travel away from me, but it'll replicate that sort of up and down motion. Everything's going to kind of vibrate up and down. So a transverse wave is a wave where the material is being displaced, the vibration is one direction, and the wave travels perpendicular to it. So transverse and perpendicular are kind of connected here. So the velocity of the wave is in one dimension, but the material vibrates up and down in a perpendicular 90 degrees away. So that's what you would see as ripples in a pond. If someone's like swinging a rope around or something like that, that would be a mechanical wave that's transverse. Some waves that travel from earthquakes, seismic waves, are also transverse. They actually ripple the ground. The second type of wave motion is called longitudinal, and longitudinal is where the sound comes in. Longitudinal waves are compression waves, and as you can see in this diagram here, the person who's very, very eager is compressing the slinky to the right, which causes a squished region, and then they can pull it back, which causes a stretched out region. And as you push it in, the slinky doesn't want to be compressed there, so it tries to push itself away, and that causes a ripple down the line. I don't know if this is going to show up too well, but if I've got a slinky here and I give it a quick push, a ripple will go down it. Again, it's hard to do on these webcams. But it's shown here in these areas of high and low compression, and that area of compression is what is actually traveling one way or the other inside of the slinky. Now, for sound, as a longitudinal wave, it's going to be these compression waves, but it's going to be in the physical material of air. So sound being a longitudinal wave, it's produced from alternating high and low compression areas in air or other materials. Some of you may have noticed in literature and other places that some of these areas were called like a rarefaction. I never write it because it's so hard to remember how to pronounce it. Because the air is rarefied there. It's rare. It's not very common. I don't like the term. I like saying low compression. But rarefaction, you can spell check me on that. But these alternating areas of high and low compression are what create sound waves. Our ears detect it because, just remembering, I saw a good video on how ears work. I should probably link that in there. So as high compression of air hits, it causes our eardrum to push in, and that causes the fluid in our ear to move and all the other stuff to get pick it up. I can't remember the term off the top of my head right now. I want to say cilia, but I don't think that's right. And that's how we pick up the sound waves, and our brain interprets that. But it's all compression. So in this picture here, I've got a tuning fork. And the tuning fork, if you hit it, little vibrations are going to travel back and forth, and it's going to wiggle. And as it wiggles, it pushes on the air back and forth. It causes it, when it pushes out, it produces high compression. When it pulls back, it produces low compression. And those ripples are what we pick up as sound. Now, sound waves visually are kind of hard to see. So let's go ahead and see if we can take a look at a demo here. All right, so here we are on one of my favorite websites, PhET. And we're looking at the it's the waves intro demonstrated, but there's water waves that can produce sound waves, light waves. Sound's what we want to talk about. So right here we have a speaker. It's a cone speaker. And I can this little button, turn it on and off, and it's going to show dark and light areas alternating to represent waves. Now, if I want to put it in slow motion or pause it, here we go. So right when the cone gets pushed forward, there's a white spot that represents high intensity. So they're using color to represent intensity of sound here. But when the speaker moves over, it produces a high compression area that's kind of like a crest of a wave. And then, put in slow motion here, when it pulls back, speaker pulls back away, it's kind of pulling away from the air, and it's kind of spreading the air out, and that's going to be a low compression area. And sound travels out like ripples in a pond, like water would. So if you were standing over here, you would be detecting those high and low compression areas in your ear. Now I've got it at it's very low speed, low frequency and everything. But let's take a look at what would happen if we had air molecules instead of having this kind of light and dark area corresponding to crests and troughs. So nicely enough, it's got this particle simulator here. And here there's a bunch of little white dots that represent air molecules. Red dots represent air molecules as well. But it's hard to see what's happening to the air molecules once they start moving. So the red dots are there to represent a grid. And the idea is that when a wave moves from one place to another, the physical materials may vibrate back and forth, but it's always around a central area that they return to. So you'll see the red dots wiggling right now. That's just because they have energy and they have temperature. But once a wave is produced, click the speaker on, you can start to see these kind of ripples and compressions of the wave. The wave producing compressions of the air molecules as they move away. So the speaker was retracted, so there's a rarefied area there. If I click forward, as the speaker's compressed forward, it's producing a squishing of air molecules. That represents a crest. Now, go ahead and let it keep going. You see these ripples passing out. They seem more intense close to the speaker and not so intense further out, which is the way it's supposed to be. Sound gets weaker the further away you get from a speaker. But this is a good visual representation of what's really happening with the air molecules. They're moving around, but they're going back to where they were. So when you turn on a speaker, the air's not being shot out like water out of a hose or something. The air molecules are just vibrating because the speaker cone's going back and forth. And I got some videos linked on Canvas to help you out with those visuals of speakers. Now, one big quality of how the air molecules move has to do with their temperature. So in that simulation, you could see that the air molecules were actually wiggling around when there was no sound. As air gets warmer, the air molecules wiggle around more. They have more kinetic energy. And so as they're wiggling around more, they're more likely to interact with each other. So sound actually travels better in warm air. It travels bad in cold air. So the colder the air, sound doesn't travel as well, warmer it does. And we have a formula for that. And we got it on the screen right here. It says that the velocity of sound in air is going to be 330, which represents the meters per second for the velocity, plus 0.6 meters per second for every degree Celsius that you're at above zero. So 330 would be the velocity of sound in air at 0 degrees. So if it's freezing cold in the Celsius temperature scale, water freezes, that's how fast sound would travel in air. But as it gets warmer, sound travels better and better and better. So let's go ahead and practice this. So room temperature air is about 68 degrees. That's what you should have your thermostat set to in the wintertime so that it's not getting too warm, not using too much energy. But that's 20 degrees Celsius. So if we're at 20 degrees Celsius, I want to figure out what the velocity of sound in air is. So let's go ahead and use this formula and try it out. I've got in that equation, I'll go and rewrite it. Velocity of sound in air is going to be 330 plus 0.6 times the temperature Celsius. And for us, the temperature in Celsius is, I always think there's like another S in Celsius. I'm terrible at spelling. So the temperature in Celsius for us is going to be 20 degrees, and we want to find out that velocity of sound in air. So let's go and calculate it up. Be 330 plus 0.6 times the 20, and that would give us 330 plus 12. So the velocity of sound in air at room temperature, traditional room temperature, is going to be 342 meters per second. Now, in some of the problems we've already seen, I referenced the velocity of sound being 340. In one of the Hewitt-Drew videos, he referenced 340. Well, it's easier just to work with 2 digits than 3. So 340 is kind of what we use by default. I guess that would be closer to like 66 degrees or something. But 342 is what we would get from this formula. Now, we could solve backwards for that. We could figure out what the temperature was as well. But we'll go ahead and take a look at just using that for now. Now, also, like we have with any of the waves, we use just standard old wave ideas last week, that there's an equation for the velocity of a wave that depends upon the properties of the wave, that are frequency and wavelength. And when it comes to sound waves, what's important is that if sound's traveling through air, it's going to have that velocity like 342. That's going to be a constant as the sound travels. So if you modify the frequency of the wave you create, you're going to change the wavelength. So in terms of proportionalities, the velocity is going to be lambda times frequency. So if I am playing like a flute or a saxophone or whatever, a guitar, and I produce a sound that is vibrating the physical material and vibrating the air at a higher rate of frequency, so more vibrations per second, if F increases in this formula right here, the product of frequency and velocity has to stay constant. So if frequency goes up, the product of wavelength and frequency has to stay constant. So if the frequency goes up, the wavelength has to go down, which means the waves would be closer together. Now, if I'm going to draw waves and I want to write more, so let's say I have like waves that look kind of like this. If I wanted to make more waves per second as I'm writing them, I would have to squish them together, make more waves per second. So as I do that, the lambda value gets smaller, and that kind of makes sense. So if you make more waves per second, you get shorter waves. Let's go and take a look at a couple of example problems here. I have the answer off to the side here so that you can take a look at it. But how about you go ahead and see, let me scroll down so my face is not covering up the answers. How about you pause the video and see if you can kind of figure out what the answers are, and using the information that we had above, so you can always rewind the video a bit and take a look at that. Okay, so example 1 says, if a bass note has a frequency of 30 hertz, what is its wavelength at room temperature? Okay, well, I don't know much about bass at room temperature versus freezing or sweltering hot summer days, but here I'm being told that the frequency is 30 hertz. I'm being asked to find the wavelength. So the only thing that connects those two together would be the velocity. And that's where I need to, kind of go back up and see what we had up above there. The velocity of sound in air was 342. So that's something that I'm having to reference here. So 342 meters per second. So using that information, I can now use the formula V is equal to lambda times F. I can put in 342 equals lambda times 30, and then I can solve for the lambda. Now as I'm doing this, I'm wondering if I actually use 342 or if I use 340. I'm feeling a little scared here. Oh, I use 342. So I get 11.4 meters for the wavelength. Those numbers seem familiar, like we did them in another problem someplace. In example 2, it says, what would happen to the length of the bass note's wave if the temperature were to drop to freezing? So I have here that the wavelength would be shorter, but let's go ahead and figure out what the answer would be. So we still have the same frequency, and I'm still being asked what's the wavelength, but now the question is, what's the velocity? Because I'm not at 20 degrees, I'm not in regular room temperature air anymore, I got to calculate what the velocity is. So first up, I see the velocity of sound in air is going to be 330 plus 0.6 times the temperature in Celsius. And so that would be 330 plus 0.6 times 0. So the velocity of the sound in air is just going to be 330 meters per second. Now that means the sound's traveling slower, so as I make waves, they're not going to move as away from the source as far, so they're probably going to be squished a bit. So let's go ahead and prove that that answer is going to be less than what we had before. So let's go ahead and get lambda. So the equation, standard equation for the velocity of a wave based upon the properties, but now I'm using 330 meters per second, and I've got lambda is my unknown, 30 hertz is my frequency. I divide by 30, get a little low on the screen there. So 330 divided by 30 would, divided by 30, not 33. 330 divided by 30, and I get 11. So as the air gets colder, the waves actually get squished together a bit more because they're not moving as fast away from the source. And if the temperature were warmer, the waves actually get more spread apart. So that's a quick little overview of some of the ideas behind sound. Not quick, but relatively quick. I will have some other videos posted, kind of cool things to take a look at in terms of mechanical waves on Canvas, so go ahead and check those out.